Thanks a lot for the introduction, and it's my pleasure to present my research today. And so the title of this presentation is Generating High-Level Knowledge-Enriched Maps Through Observing the Environment and Its Usage Over Time. So first, a little bit of a background. Why do we need more or robots in general to help us with different tasks? And so there are two reasons. One is, or not just, but I focus on two reasons. One is like the shrinking labor force. And so as the population is aging, there are more and more people that can work. And so the labor shortage will lower the economic growth by 0.7% points annually till 2025, and then 0.9 points afterwards. And so in order to tackle these problems, robots could be a vital role to overcome this. And another thing is like with the aging population. So for example, 1/3 of Japan's population is aged above 60. And if autonomous robot could help them during their daily life, that would increase their quality of life by a lot. So for example, like people who are too old to drive by themselves could use autonomous vehicles, and that would help them a lot. But what is the big problem? So why don't we just use the robots and we're done with it? Because at the moment, there are already robots used a lot in factories. But there is a big difference, because for the current usage of robots, it's, for example, in the left top picture, you see from an Amazon warehouse, where you have all the robots driving around and carrying the items to the packers. And it's like very high level of autonomy that is existing there. On the right pictures, you have these production lines where where the robot just constructs the frame of a vehicle and do like various tasks. But the thing about these examples is that the environment they're employed in is very well defined. So for example, in the left pictures, maybe you can see a little bit on the bottom or on the floor, the lines that are drawn there. So the robots can just use the lines to navigate, or sometimes, or there's often QR codes, which tells them the exact position they're in, and so on. So it's like the environment is made for the robots to function. And often also the place where the robots are employed is separated from humans, especially for the production lines. It's basically walled off, and often if you go in, then there is like a security that already shuts off the robots. But if we really want to advance the usage of robots, we have to employ robots in a shared space with humans. So of course, like for care of elderly or for like service robots, they need to interact with humans, and so they need to be in the same space as we humans are. And the same also goes, for example, for self-driving cars. The self-driving cars now have to interact with human drivers. They have to identify the pedestrians and react to what these humans are doing. And so it's a whole different level of difficulty between how robots are mostly used currently and how we envision that in the future. And so to go a little bit more into it, so for example, for the task of self-driving cars, For a self-driving car, first, it has to find out, okay, where am I currently? So, for example, in this case, it has to find out, okay, now I'm currently in front of this crossing and this is my place. Then a very difficult task is to recognize the scene around it. So are there any traffic lights? Are there pedestrians? Are there other cars? This is like the second task, and the third one is that the planning, how to safely interact with all of the surrounding. And because like also these environments are highly dynamic, this is a very, very difficult task to accomplish. And so how to make this task a little bit easier? And one of the ways that is mostly used is to use semantic maps or to use local dynamic maps. So, and on the bottom right, you can see sort of several layered map for self-driving cars. So first we have like the permanent static, just like how the roads go. And then also maybe one layer just with the traffic signs and so on. And then for the top layer, just like the highly dynamic, like the vehicles, pedestrian, and so on. But for example, these maps sometimes need to be very, very detailed. And in the case for self-driving cars, it's not enough to just see what maps that are available on Google Maps and just use these, because they lack too much information. So first, sometimes they're not, the accuracy is not high enough. So that if you would use like a GPS signal, a very accurate GPS signal, and compare it to the map, then sometimes there's some difference. But you also need more information. So which are the lanes? Which lane is for turning right? Which one is for turning left? Where are the traffic lights? Or are there even traffic lights? And because of this, this generation of maps is very tedious and also very expensive. And in my presentation, I will focus on how to make this generation of maps in a more autonomous way. Because another trend that is currently happening is that the amount of sensors that are used throughout all of the disciplines is increasing very quickly. And so, for example, you have also the Tesla vehicles equipped with sensors, and they're constantly observing the environment and constantly collecting data. And sort of this goal is to use the collected data, to utilize the data gathered by these vehicles, and then add more information to the environment. And so this could be, for example, like semantic knowledge, like which is the road, where is a sidewalk, or it could be about parking spots, where are parking spots, but also apart from these autonomous cars, also for example, construction fields, how to get more knowledge about the construction fields from the data. And the overall goal is so that we get a very good map about the environment with these semantics, so that the robot doesn't have to just from the sensor data directly understand everything, but can rely on a given map so that it can rely on prior knowledge, so that it's much more easy for the autonomous robot to first know the environment itself, and then, of course, because of the better understanding, to react better to it. So in this presentation, I want to go mainly into three different topics. One is parking spot detection, then large-scale semantic mapping, and semantic mapping of a construction field. And I would start with parking spot detection. So parking, of course, is also an essential part of autonomous vehicle. And that kind of means it also has to know where are the parking spot where I can park. This is one part, but the other part is, say, maybe we already have given or we established then a map of where the parking spots are. It would also be very helpful to have some prediction of where are parking spots available. And so, for example, probably all of you know that have a car, you drive around in the city and you're just searching for a parking spot. You just want to park your car and get off of it. And it's very common. So according to one study, nearly 30% of traffic in cities is caused just by drivers that are searching for a parking spot. And if you will have an app that just says, okay, probably if you turn right here, there's like a high chance that there is a parking spot, that would definitely be very, very helpful. So what we did in this research is we used this autonomous electric vehicle that is also equipped with LiDAR, a Velodyne 32 LiDAR. And we just drove around on this path in dark blue. And just from observing the environment, especially if some cars are already parked somewhere, we then estimate the whole or a map of all the parking spots and parking areas around it. And we drove the same path not just once, but 10 times. And then we not just get the map of where parking spots are available, but also the occupancy rate, or how, for example, from the 10 runs, how often a car was parked there. And so, for example, for the map of a university, and if the spots are assigned, you could see, okay, this person always had his car parked there. So he must be like very working a lot because he's always at the university. But let me go back a little bit more about the idea that we were using. So how to detect these parking spots in the first place. And I mean, of course, first, maybe what you would think is just to use like these lines that are printed on the road to detect this. By detecting then these lines, you can detect the parking spots. But while this often could be used, it's not always possible, because at the same time, sometimes you have just some parking lots where it's just some gravel and there's like the actual parking spots are not really really marked. And for this, we basically say that at the moment, it's not just the autonomous cars, and it will not be for the foreseeable future, but it's a mixture of also human drivers and autonomous cars then. And so we can just learn from the human drivers, like where do they have parked their cars, and then use it as an indicator, and from there estimate the whole structure of the parking lot. And so basically for that, are some of the related works. Like, as I said, mostly they employ the line markings on the road. For example, from a fisheye camera on a vehicle, or from some surround view images. But there are also some who employed other vehicles. And on the bottom here is a picture where they used vehicle detection from 2D LiDAR. But yeah, as I said before, the vehicle that we use is this autonomous electric vehicle equipped with a lot of different sensors. But for this research, we only use the Velodyne LiDAR. So maybe first, what the data looks like that we get from the LiDAR data. And on the left side, you can see one image of the LiDAR scan. So the own vehicle is in the middle, and basically it measures the distance to hundreds of thousand points in the surrounding, and give the depth or the distance to that point. And so what you get then is like a point cloud. So just points with the X, Y, and Z axis. And you get, so the Velodyne gives about like 10 Hertz, so 10 of these scans per second. And we then use them to first detect cars in the surrounding. And then from these cars in the surrounding, in combination with occupancy grid map that we use, we then predict the parking lot topology by a graph-based method. So this is basically, this method can be separated in 3 modules. First, the mapping, then CNN-based vehicle detection module, and third, this topology estimation. And so for the mapping, what we use first is we just use SLAM, so simultaneously location and mapping algorithm, for the point cloud data. And sort of this is the result. And the different colors are based on the height of the point. And then we first just detect the ground surface. And for that, we also using from our own vehicle, we know like the ground where our vehicle has passed, and a region drawing to just get the surface. And for that, from that, we generate an occupancy grid map. So where white means, okay, this is a free space, black is our obstacles, and gray is basically unknown. We generated for one run, but for example, like parked cars on the right are detected as obstacles, and sort of these, to remove these dynamic objects and also some noise, we fuse multiple runs and get a much more nicer occupancy grid map. So this is like how we then first get this map of the surrounding. And then the second module was the vehicle detection. And so we employ a CNN that uses elevation images that are generated from the LiDAR data. I will go into that in the next few slides. And then we still have to refine the results and to get rid of multiple detections or false detections. But first about this elevation of this CNN. So this is also, for example, an example of the point cloud that we get from the LiDAR. On top, you can see the image of the scene, and on the bottom, what the point cloud looks like. And then basically, we zoom out and view this scene just from above, just really from top down. And then in the next step, we lay a grid over this scene. So in X and Y. And in the next step, we say that, for example, this grid, each of the cells will become a pixel in one RGB image that we generate. And basically, we have on the bottom, like for one part, enlarge it a little bit. And for example, one cell, there can be several points in it. And then we get the maximum height value of this cell, the minimum, and the median. And so the maximum value will then be our R channel. The green channel would be the median height, and the blue channel the minimum height. And the reason why we use this kind of 3 channels is that conventional CNNs that are used on images are also with 3 channels. And so basically, if we then also have the 3-channel representation, we can make use of these methods. And this is basically what we did, is then we construct this bird eye view image, and we run faster RCNN with the backbone of VGG16. And basically, this faster RCNN first gives proposal on where an object might be, and then also gives a classification network, says if it's a right proposal or not, and then also gives the direction of it. And so this worked quite well, and this was then also just for the detection of this vehicle using this bird eye view was also we also published that. But so this is just how we detect the vehicles. But because like we run this vehicle detection for each of the scan, we get for a parked cars, like not just one detection, but every time while we pass, it gets detected. And also sometimes we get some false detection. And in order to filter that out, we use a method called density-based spatial clustering. And with this, we can get a much better result of the actual environment. Though sometimes it's not 100%. So for example, in this red box on the bottom, you see that it also filters out a few of the true positives. So then we get like this vehicle detection of the parked cars, and we have our map. So the next thing is then how do we estimate the structure of the parking lot, the underlying structure. And this is like the third module. And so what we basically do is we look at these detected vehicles and see how are they connected. So for example, two cars that are parked side by side, or we have two cars where in the middle there is some distance between these. So two cars side by side, but with a vacant spot in between. Or are they parked more in a row that we have, for example, here, these two are parked sort of nose by nose, and same nose by nose, but with a vacant spot to it. And so what we basically do is try to find sort of parking lines. So for example, here, these two were parked side by side, but with a vacant spot in between. So probably there you should also be able to park. And then you see that on the bottom here, there is like a large space with no obstacles. So then we see, okay, there's a parking line, and we just extend it because there's no obstacles. And next step, then we just straighten the parking lines, because I mean, also when we detect the cars, they're not always, some drive more into the parking spot than others, and to get more or a good view, and then predict driving lanes. So every car has to be able to get out of this parking spot. And so for the results, we analyzed 6 different areas on 10 different days. And through the graph-based approach, we could increase the amount of parking spots by 57%. And with 10 trials combined, we could completely reconstruct the parking lot structure of 4 out of 6 areas. And yeah, then with 10 runs, also the occupancy rate. So here you can see like the results just for the single runs, and then the combined ones. Here it's more for the results shown that in blue, the parking spots that are occupied. In green, how much we can infer just for the single day. And in red are then falsely inferred spots. And so you can see that for most of the times we are able to at least infer some parking spots. Yeah, so this is then the area, or the result overlaid to an aerial picture of the investigated area. So this was for one area from the university. But we also did the experiment just in a suburban environment, and also got quite nice results. And also, before, this was the data we gathered by ourselves, but we also tried it out with data from the Rosbeck stores from Tahara area, and yeah, the results also look quite nice. So basically, this research showed, just from driving around, just from analyzing the LiDAR data, then we can get quite good knowledge about parking spots in the area, and then an autonomous car could use this information to find itself a parking spot, but also if it's often observed by passing cars that are equipped with these sensors. For example, a live map of available parking spots could be implemented. Then I would like to go to a second topic I want to talk about, large-scale semantic mapping. And so as I said before, autonomous cars need like a very detailed understanding about the environment. And for example, if we can create a semantic map, so semantic means that each color represents a different class. So the dark purple is a driving road, and the pink is sort of a sidewalk. And if we can create such kind of map, this would have a lot of knowledge or lots of meaning for the autonomous vehicle. And how can we do the reconstruction? And we can use a camera-based approach or LiDAR-based approach. So the segmentation results for cameras are mostly better, but the reconstruction results are not as good because you have to estimate the depths either from stereo cameras or from structure to motion. Whereas LiDAR-based have an excellent reconstruction, but the segmentation results are often not as good. And so in this research, we basically fused the camera-based and LiDAR-based method. And basically, how we do it was we have the LiDAR data and the camera pictures. For the camera pictures, we are using deep neural network, get the semantics, and then we project the LiDAR into the camera plane so that we can connect each point with the color from the image and also the semantics. And then use SLAM to get some 3D mapping. And this map would already have the semantics that we extracted from the pictures. However, they are quite noisy. And so then we reclassify, or we improve the semantics by reclassifying them. And we tried two different methods, a random forest classifier and more deep neural network, the sparse convnet, to get improve the results. Again, we used this autonomous electric vehicle and used the LiDAR, but this time we also used the Ladybug camera, which gives us 360-degree video streams and it has 6 cameras, which each 5 megapixel. And yeah, so first about the synchronization between the camera and the LiDAR. So a LiDAR measurement is not, for a camera, it's basically the shutter goes down and in that moment it takes the pictures, whereas the LiDAR, it rotates around. And so from the beginning of the scan to the end of the scan, it takes 100 milliseconds. And during this 100 milliseconds, the car, of course, moves. And so we have to account for that. We basically do that to interpolate the vehicle positions using the timestamps from the image and from the lidar. And so, for example, before the synchronization, you can see that the pole here is a bit off, and after this, it fits quite nicely. However, for example, for the car, it's not just the motion of our own vehicle, but the other cars also moving. And so that even though we account for our speed, there is still an offset because of the motion of the other traffic participants. And we tackle this by reclassification, so by using the random forest. So how do we refine the segmentation results? And we use two different methods. One, random forest, with a lot of features that features that are defined on the bottom, and also we tried the sparse ConvNet. Of course, this method needs some training data, and for that, from the data we gathered, we annotated 5 meter times 5 meter tiles, and 105 tiles for training and 105 for evaluation. We also used a polyscape dataset to pre-train the sparse ConvNet, and by using these two methods, we could quite improve the results quite significantly. So just by the projection, we only had like an IAU score of 38.9%, but then using the reclassification, for example, the random forest, we get an IAU score of 65.6%, and it outperformed the deep learning method quite significantly. And probably this is because even though we annotated quite a few tiles, that's still rather sparse data. But here I want to show some of the results, how it looks, the final result look like. On the bottom left, you see the colored point cloud of the scene, and then in big you see the semantics. So here is the driving road. On the two sides you have a sidewalk, a lot of trees here, and then some signs. But how can we use the information that we generated? And for example, from the scene here, we could remove the traffic, so we have a better view on the street itself. Or then we can also remove the vegetation, because all of the points are classified, and see what would the city look like without any vegetation. But another one is, for example, we also measure all the vehicles and pedestrians during the runs. And so that means we can just say, okay, give me all of the points from vehicles. And you can see that how the lines of how the vehicles are moving. So from that, you could estimate how the lanes are going, or with the pedestrians, you can see, okay, here's a road crossing, and so on. Yeah, so basically, this is what I wanted to share about the second topic. And I think it's very nice to see, for example, these, see how the cars are moving here. And yes. Okay, so for the last topic, the semantic, like mapping of construction fields. And so also, as said before, there will be more labor shortage. And so many fields are investigating the employment of autonomous technologies. But it's also very difficult because, for example, construction sites, they have their own rules of layout, and it's not, I mean, on the streets, you have at least some lane markings and so on, but on construction field, there are no such thing. And if we could create a semantic map from daily measurements of the field, we could infer like how the construction field is used. So where the construction material is located, where the usual parking spots for dump trucks, and so on. But yeah, if we just use a single measurement, then it does not necessarily reflect the underlying semantics. It could be that just one time a dump truck is parked in that place, but usually you cannot park it there because then you block off some parts. It's also a very cluttered environment. So it's difficult to see where the different objects are and segment them. And yeah, so what we do in order to solve this problem is we use UAV to measure point cloud data or depth, a height of the field, and we acquire this data on several days, and from that we get first a ground plane of the environment, and then detect objects that are above the ground. And these objects are basically the dump trucks or construction vehicles. And next step, we classify them, and we have then this classification over the several days. And from that, we cluster them and construct a semantic map. The ground plane estimation is basically we extract the ground plane for each of the run, and then fuse it together to get a better result. Once we have the ground plane, we first extract all points that are 50 centimeters above the ground, and then just use Euclidean clustering for the objects. However, this does not always work well because sometimes, for example, vehicles are parked very close to each other, and so just a Euclidean clustering gives a bunch of construction vehicles as one cluster. So basically, here's like a line of 6 different backhoes that are just clustered together. And in order to overcome this problem, we introduced a height-based computing object algorithm proposal. And what it basically does is, for example, here we have 3 backhoes clustered together, and it removes the points close to the ground until this big cluster can be divided into 2 subclusters. And this process is then continued until the end. Okay, and so basically for each of these subclusters, we give it to the classification network and get an object and the score. And the combination that gives the highest overall score wins or gets assigned at the ground truth. And so, for example, in this case, the highest total subscore would be the combination of the 3 backhoes. And yeah, but then we also, for example, how are they scored? And we basically use two different methods. One is CNN based, and also one is random forest based. For the CNN based, we first generate a picture out of each object, where we assign like the R channel to the height above ground, the height difference between points, and the blue channel angle in Z direction. We trained then on different architectures, VGG19 exception, and yeah, the other method we tried is a random forest. And yeah, as I said before, so these are then, for example, the results for all of these pictures. So for example, the top picture is like, says classification is noise with 0.58 probability, where here you have with a 0.85 probability that this is a backhoe. And you let them compete against each other, and basically the winning probability is that there are 3 backhoes. And so on top we have like the result without subclustering. In the middle, the manual click subclusters sort of protrudes, and on the bottom the result from the competing subcluster result, and gives quite a good result close to the ground truth. And then this is like for one day we get the results, but we want to get the underlying semantics, and for that we fuse multiply daily data, where each of the, for example, for construction vehicles, each is assigned a potential field. We add the potential fields over many days, and then use a threshold to get the predicted areas. We ran experiments on the Sapongi field and the Kami field, and the measurements were done over a large range of time. For example, here in April, the ground is still snow covered, and where in August it's like very different season. And yeah, we can get quite nice mean IUU score for the classifications, and we can also show that the subclustering works quite well compared, for example, to using of no subclustering or maximum subclustering. And yeah, here on the right you see the results of the semantic map, and this could be, for example, used for a dump truck comes into the area and wants to find a parking spot. So first you can see, okay, where do dump trucks usually park? So this yellow area, and then the path can be planned that avoids all of these regions. And we can also see, like, for example, the change over time. So recently the Sapongi field is expanding on the northern field, and so before there were like a lot of vehicles parked, and this was constant use, but because of the change is about to come, now the area is completely free of any objects. So yeah, in this last one I presented just how to create semantic maps for construction field, how they're used. And with that, I would like to finish my presentation. Thank you very much for listening, and I think now I'm gonna have a little bit Q&A session if I'm not wrong.